Okay, so in this session, we're starting with chapter 16, part 4. And hopefully, I'm doing the 3 point check real quick. I can see that it's recording. I can hear myself, or it looks like the mic is responding, and I think I'm sharing my screen. Okay, so for this part right here, we are looking at the strong bases. So we just covered acids, strong acids, weak acids. Now we're focusing on strong bases in the chapter as we begin to power down towards the end of the chapter. Okay? When it comes to bases, right? Chapter 16, part 4, when it comes to bases, we tend to identify strong bases by using this format here metal hydroxides. Okay? So with the metal hydroxides, we tend to look at strong bases as group 1 and group 2 hydroxide. So let me write it down here. Group 1 and group 2 metal hydroxide. So what I mean by that is the metal is going to be lithium from group 1, potassium from group 1, sodium from group 1. So I'm not writing this in any particular order, right? But if you add the hydroxide ions to it, you get essentially the strong base. Okay? Cesium. And so from these, actually, let me erase this right here so I can actually write the formula of the hydroxide. The hydroxides are lithium hydroxide, potassium hydroxide in no particular order, sodium hydroxide, and then cesium hydroxide. Okay. Yeah, someone is pouring cereal. Anyway, group 1 hydroxide right here. Okay, and so we can see our example right here, potassium hydroxide, sodium hydroxide, once again in no particular order. When you're writing the formula, I grouped them together in the same group because you see that these are all positive ions. They have plus one ions, right? So to make a neutral compound, which strong bases are neutral compounds, you need one hydroxide. So the positive charge has to balance the negative charge. So LiOH, KOH, NaOH, CSOH. What about group 2 hydroxides? Let's see what group 2 hydroxides look like. Uh, Group 2 metals, and then this is the hydroxides. Because they're group 2, they all have a charge of 2, right? So calcium 2 plus, magnesium 2 plus, I use barium 2 plus, okay? Since hydroxide is still only negative, to make a neutral compound, you need twice the amount of hydroxides, right? To neutralize the positive charge. So you can view it that way, or you can do the crisscross method to get calcium hydroxide, right? Magnesium hydroxide, barium hydroxide, and then finally, oh well, I'm just going to go with the three because I'm running out of space already. Once again, you see that with the group 2 hydroxide, you need twice the number of hydroxide to make a neutral compound. And this is the representation of group 2 hydroxide. Okay, then we're moving on and talking about the definition of the base. Now, we saw from before that there are three definitions of the base, right? According to Arrhenius, I'm going to call it here R. According to Arrhenius, the base releases OH ions in water, right? So the base has to have OH ions in the formula, like we see right here. The OH has to be visible in order for it to actually be released in water. But when it comes to Bronsted-Lowry, so I'll abbreviate it as BL, Bronsted-Lowry, the duo, when they talk about the base is, remember in the Bronsted-Lowry, you have the giver and the receiver, or the donor and the acceptor, right? The base is the one that accepts the proton. Okay, I bring this up here just because in this picture here, this picture I feel like represents Arrhenius' definition of the base because it's so obvious in the example they're using that you have a base that follows that mole format, right? Sodium hydroxide. And you can see the hydroxide from the beginning in the formula. And then of course, being in a strong base and a strong electrolyte, that means when the whole compound gets in water, the hydroxide, the base ion, will completely separate from the sodium. Okay, so let me see how many amounts of sodium hydroxide they use in the beginning by counting the hydroxides, right? We have one, two, three, four, five, six. So I guess they use 6 amounts of sodium hydroxide. And so if we have six OHs, we should also have 6 sodiums, right? Because it's a 1-to-1 mole ratio in the reaction. One, two, three, four, five, six. Correct. Okay. So in other words, what I'm saying is they use 6 of these formulas, 6 of these, to produce 6 sodiums and 6 hydroxide in water. Let's see if the picture here, this is more like the mental model using the molecular level or the atoms and compound level. This is sodium hydroxide, and the sodium looks like it's the purple part, and the hydroxide is the red and white sphere. So I'm going to count this again. One, two, three, four, five, six. They use 6 amounts of these, right? 6 of them to get 6 hydroxide. One, two, three, four, five, six. Why do I bring this up? Because this is a group 1 metal, so you have a 1-to-1 mole relationship or 1-to-1 amount relationship between the positive side and the negative side. Okay. Okay, so the second definition, or the second bullet point we have here, though, they're not using Arrhenius' definition. Arrhenius' definition was used in the picture. In the second bullet point, what I think is they're actually using Bronsted-Lowry definition. That's why I defined it here. Let's see what they say. The stronger the base, the more willing it is to accept the hydrogen ion in water. Look at that. Arrhenius never said the base was accepting anything. Arrhenius said the base was releasing hydroxide ions. So in the second definition here, we're seeing a Bronsted-Lowry reference to what the base is. The base is the one that's willing to accept the hydrogen ion. So here, this bullet point here is talking about the base from the point of view of Bronsted-Lowry. And then once again, it reached a point in my journey of learning chemistry where I realized that I should judge the elements, the molecules, the compounds based on their role. Like you have one thing as a chemical to do. Are you doing it well? If you're doing it well, you judge as strong. If you're not doing it well, you judge as weak. You're still doing it, you're just not doing it very well. So here we're told the stronger the base, right, according to Bronsted-Lowry, the more willing it is to accept the hydrogen ions in water because a base's identity, or how should I say it? A basis identity is according, I don't use the term base, according to its willingness to accept the hydrogen ion. If a chemical is willing to accept the hydrogen ion, it is judged as a base. The more it is able to do that, the stronger it is. Okay? And of course, in this case, when you write out the equilibrium reaction, water will be the one acting as the acid. Okay, so moving on. For ionic compounds, or sorry, for ionic bases soluble, practically all units are dissociated into hydroxide ions or accept hydrogen ions. Once again, it's those hidden information, right? What they're saying here is when you're dealing with metallic bases, like, the MOH bases, practically all of them are dissociated. In other words, this is 100% ionization, okay, into hydroxide ion. The group of the 3 definitions of bases, Arrhenius is the one that says the bases release hydroxide ions in water. So this is kind of referring back to Arrhenius' definition. Or accept hydrogen ion. Once again, now we're back to Bronsted-Lowry, right? Do you have to understand them switching back and forth? No. But I'm just noticing that they're doing this and pointing it out to you. If you feel like they're kind of all over the place, it's because they are. Okay? So strong bases are strong electrolytes, just like strong acids are strong electrolytes. In water, these electrolytes will completely ionize, as in 100%. We're told here soluble multi-hydroxide strong bases completely dissociate in water. Okay, once again, if you have a compound like calcium hydroxide, even though it has multi-hydroxide, right? 2 hydroxide, you can say dihydroxyl, This will completely ionize in water to release the calcium ions and the hydroxide ions. Of course, there'll be two of these, right? Should have written that properly. Plus 2 hydroxide. Anyway, let's move on to see what comes next. So here they're trying to compare the monohydroxyl base versus versus the polyhydroxy base. So our example for the monohydroxy is KOH. This is the group 1 metal hydroxide that has been chosen to represent group 1 members. And then let's see, what did they choose for group 2? I'm thinking it's calcium hydroxide. Yep, calcium hydroxide. Let me show you guys both. And just like we did before, we will use the ice table, right? So for group 1, we're going to be using the metal hydroxide. K will be the metal. And remember, when we talk about the base in water, the water is implied for the strong base. Don't use the water in the strong base. So what I mean by that is you put AQ here. Oh, sorry. I just said don't use the water, right? And I'm about to use the water. Excuse me, y'all. Sometimes my mind just gets caught up somewhere. Okay, so use K plus OH. Okay. Now, if it's a strong acid, you can use the water if you want. If you don't use the water with a strong acid, you're fine. Okay. So like I mentioned before, we're going to be using the ice table. And so what we're going to do here is we're going to look at pH of strong base versus pH of weak base. I have to remind myself I'm talking about base right now, not acid, right? Okay. Our initial amount was zero point 0.1 molar. Let me make sure that was the case. I think it was zero point 0.1 molar. Yeah, zero point 0.1 molar. And then let's see how the pHs are different. Like we said before, initial is before any change has taken place, so the amounts here are 0 and 0. And then the change happens. Since this is a strong base, I want to write strong acid, but it's strong base. Remember, this is going to completely ionize, right? So all of the concentration here will be used up or will be processed. And since you have a 1 to 1 to 1 mole ratio, the amount that will be produced over here will be 0.10. Here we have 0.10. I can put the M here to be consistent. And so, oh, I didn't put the 0 here. Okay, let me try to be consistent, okay? It's the same number, just 2 decimal places. Okay, so all of this gets processed. So we have 0 amount remaining at the end. I was about to say equilibrium. When you have a one-way arrow, you don't have an equilibrium, you have an end. Okay? And so here we have 0.10 molar, 0.10 molar. Okay? So based on base, according to what we've seen so far, when you're trying to get the pH, you either do it directly using the H3O plus ions or indirectly using the OH ions. Okay. Once again, different thoughts come back to me at different points of me covering this lesson. So if you're thinking she never mentioned that in class, it's because I just remembered it right now. Okay. So the direct way of getting the pH, of course, is when you have the H3O plus, plug it into that pH equal negative log base 10 of H3O plus formula, and then you get the pH. But now we're trying to get the pH having OH. So this would be the more indirect method. Okay. So I'm going to erase this here because I'm trying not to write too much. Feel free if you're watching the video to rewind, pause, and then write that down. So I can't get the pH directly from this, right? But the ion that will help me indirectly get the pH will be the OH ion. The second best thing, the next best thing, OH ion. But this will help me get the POH, okay? So negative log base 10 H3. Oh, see that happened? See, that was so close. My brain went to what is it called? Routine mode and then just messed up. OH minus. I need to focus. So yeah, POH is negative log base 10, then OH minus, because remember the P stands for negative log base 10. So I'm going to plug in this number, negative log base 10 of 0.10. Oh, let me go grab my calculator. Okay, and I am back. So I'll put a negative here, log base 10 of zero point 0.1 molar, close that, and I get 1. Okay. Now, I was given feedback by my students that this process is a lot easier to figure out the pH than getting the kW. Okay. So I'm going to continue with this process. pH plus POH equal 14. Therefore, pH is 14 minus POH. But we already got POH up here. We took the negative log of OH minus. So that's going to be 14 minus 1, which will make the pH 13. Okay? So let me zoom out so we can see what we did. We started off with this. This is a mono, I was about to say mono, no, it's not monoproduct, it's monohydroxyl, where you have one hydroxide per formula of the base, right? Whatever the concentration of the base compound is, that's the same concentration of the hydroxide. Because remember, this is a strong base, so we have 100% ionization of that strong base to produce hydroxide, the indirect ion, not hydronium, correct? So from here, the best we can do is get POH, not pH, but then from the POH, we can use this relationship right here to get the pH. Okay, so now I see what I did wrong. You know what? I'm just going to go back up here. I don't feel like adding a page. I know I'm being lazy, but you're fine. So right here, I'm going to write calcium hydroxide for our second one. Now, once again, this is aqueous. Don't add water. Just ionize this. You get calcium 2 plus 2 hydroxide ions. Okay. So just like we did before, you want to go ahead and do the initial change equilibrium. Did I just say equilibrium? I got a text and I got distracted. My goodness. Okay. Let me focus again. Sorry, this is the reason why I take notes when I'm doing stuff, right? Yeah, I got a text from somebody and I got distracted. Okay, where am I? Back to this. We're doing zero point 0.1 molar, y'all. It's a struggle. Zero point 0.1 molar. Let me just go ahead and do 0.10 molar just to be consistent. Okay. Initial is 0, 0, right? Now here's where ionization takes place. Okay, once again, you have to use 0.1. Use all of the calcium hydroxide you have available so that in the end we're left with nothing, right? Since you have a 1 to 1 to 2 mole ratio, that should be reflected in the change part. So for every 0.10 molar amount of calcium hydroxide that ionizes, we produce the same amount of calcium ion because you have a 1 to 1 mole ratio. That's what those numbers mean. But since you have twice the amount of hydroxide, it should reflect that here, twice the amount of hydroxide. So it's going to be plus, plus, right? To get the N, take I plus C, you get 0.10, 0.20 molar, okay? Once again, the ion that indirectly gets pH is this one here, this one here, this one here. Ultimately, is this number right here. But we don't get pH directly, right? What we get directly is POH. And POH is negative log base 10 of the amount of hydroxide at the end once ionization has taken place. So you put here 0.2, okay? Plug this in my calculator, negative log 0.2. Y'all, I'm sorry, since I'm sharing the screen, I can't really show you how I do the math. There's only so much I can do with when I'm sharing the whole application, right? But I press this right here, and this should end up being 0.699 or approximately 0.7 POH. How much will pH? We know that pH plus POH equal 14. Therefore, pH is what we're solving for. Is 14 minus POH. It's going to be 14 minus 0.7. And so we end up with a POH. Oh, sorry, pH. I got distracted by this. Oh my goodness, that is a struggle. pH is equal 13.3. Okay. So in the previous problem here, we got a pH of what? 13. Now we got 13.3. Remember the scale, right? From 0 to 7 to 14. The closer the pH is to 14, which is the highest, the most basic, the more basic it is. So this is more basic than the other one that we saw, the monohydroxyl. This is less basic. Okay, it's all relative because this is a little bit further away from 14 versus this one here being closer to 14. Okay, let's see what we have in the notes. 13.3, what they have for the first one, 13. So we got this, we can now move on. Okay, I won't work out this problem because it's not literally. It's the same problem because literal would mean literal, right? Like a photocopy. It's a very similar problem. What I'm going to do is kind of skim over it. Okay, sorry, I'm drinking some water. Once again, we have a group 1 hydroxide. This is monohydroxyl or monohydroxy, dihydroxy, as in you have one hydroxyl group, you have two hydroxyl groups here. This is group 1. You can see that metal. This is group 2 metal. So whatever you do down here, they don't even use the ice table, right? It's kind of implied that this whole compound, for every one amount of this compound, you produce one amount of this and one amount of this in the ice table. So if this whole compound is 0.255, you're going to get 0.255. And they use the KW process, right? In the end, it works out. So I'm not going to be working this part out because I'm trying to, go through this part here. But y'all see, right? Or do you guys want me to work it out? Okay. So then you're thinking, I guess I'll work it out. Let me write these numbers here. Okay, so what I'm gonna do the lazy thing and use the same tables I had from before. It's the same thing, y'all. It's the same thing. So let me write this down somewhere here so that I don't have to scroll back and forth so much. I know I'm trying to be lazy. I'm trying to push through the laziness. 0.255 is the first one. I think that was the question right there. Potassium hydroxide. The next one is 0.0015 strontium hydroxide. Okay, because the process is the same, y'all. Same process. So for the potassium hydroxide, I'm just going to go back here and change this number here. As I said, it's the same process. And this time we have, what was it? 0.255 molar. And over here I have 0.255 molar. So we can end up with 0. And then here is going to be plus 0.255 molar. 0.255 molar. Okay, 0.255. Oh, sorry, that's already added. So 0.255. Okay, let me make sure I copy the right numbers. Points. Oh. Okay, I need to capture this part. Give me just a moment. Okay, so when we're looking at this right here, let's go ahead. Oh, there are controls here. Oh. Oh, this is weird. Okay. This is so weird. This is kind of different. Okay, let's see. Can I zoom this in? Ah, I didn't know that. It's kind of weird. Anyway, let's go ahead and move on. I kind of got distracted there for a little bit. Um, I'm gonna be working this one out here. So this number here is gonna be 0.225, right? Then I got 0.0015. Okay. So I tried to work this out earlier, but let me just go ahead and erase this part. It's 0.225. Okay, I need to erase all of this. Okay. So what is the question really asking us? It's saying here, find the OH ion and then the pH of a strong base solution. What are the OH ion concentrations and the pH in each solution? Oh, I'm realizing that this is not good. Okay. You know what? Let me X out of here. Okay. So I'm going to be working on this problem right here. So to show this problem here, let me actually open a new page on the bottom. The new page down here shows that we're going to have 0.225 KOH and then 0.0015 molar strontium hydroxide. So what they want us to find here is, says find the OH, or sorry, it says here, what are the OH concentrations and the pH in each solution? So for this one here, let me go ahead and for the first one, I'll work on KOH. Once again, leave out the water. For the strong base, leave the water out. K plus OH minus. Okay. You want to get your ice table. So you're going to have your initial, your change, your end. And the amount here is 0.225 molar, 0, because nothing has happened yet in the beginning. And then you have change. In change, you're going to write the change in terms of the stoichiometry. This is a strong base, so you're going to have 100% ionization, 0.225 molar plus 0.225 molar plus 0.225 molar. Add these right here. 0.225 molar, 0.225 molar. Okay, this is going to be 0. Okay, so this ion is the one that indirectly gives us the pH, right? We can find the pOH directly though. We're going to take negative log base 10 of 0.225. Let me plug this here. Negative log of 0.225, close parentheses. I'm going to get, what is it? 0.648. That's going to be the pOH. Then the pH, of course, will be equal to 14 minus 0.648, which will be equal to 13.35. That's the pH, right? And then for the next part here, let's see, yeah, 13.35. For the next part here, we're doing strontium hydroxide. So let me go ahead and add the page here. I'll do it on this page. Strontium hydroxide. This is a group 2 hydroxide. So for this one here, you have strontium ion. This is group 2, so it's going to have a charge of +2, plus twice the amount of hydroxide, right? Every formula or every amount of strontium hydroxide holds within the formula 2 hydroxides. So, so real quick, just in case you're wondering, you can look at it like this. The central atom being strontium, and there's a hydroxide here, a hydroxide here. Okay, just in case you're wondering. So when this gets processed to be ionized, this bond breaks, there's 2 hydroxide uh, pieces in the formula. So for every formula that gets processed, you get 1 amount of strontium ion and then twice the amount of hydroxide ions. Anyway, just in case you're wondering, if you weren't, then that was just an extra piece of information. For our second one here, 1 ICE, we have 0.0015. This is our initial 0, 0 before ionization takes place, before those bonds got broken to make the ions. And then when the ionization is taking place and you're processing the molecule, for each molecule that gets processed, we have one amount of strontium ion, twice the amount of hydroxide. So here we're going to have minus 0.0015 plus 0.0015 and then plus 0.0030, correct? Because this has to be double the amount. This has to follow the 1 to 1 to 2 mole ratio. And when you're adding this, you get 0.0015, 0.0015. This is, of course, molar, 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 0.0030 molar. Okay, now this indirectly gives us the pH indirectly, but directly it gives us the pOH. pOH is negative log base 10 of that number, 0.0030. And so we end up with what? Negative log of 0.0030, close parentheses. So I get 0.0030. I get pOH of 2.5. Let's go with 2. Okay. And then pH is equal to 14 minus 2.52. So pH should be 11.48. That's our pH. Okay. So the first one was going to be that. So of course, they're asking for the hydroxide ion, right? So the hydroxide ion here is going to be 0.225 molar. That's one answer. Then the pH is at the hydroxide ion here is 0.0030 molar. Okay. That's the first one. Finding OH minus and pH. Oh, now I see where I kind of messed up on. That's why now I see where I got the 0.225. No, 0.255. I was like, where did they put 0.255 from? They messed up right here. It's supposed to be 0.225. Because in the end, to get it right, I don't know. I'm not the only one who saw that wrong. And this is going to be ours, 2.003 right there. Let's see, does that match what we have? Yep. And the pH, 11.48. Yep. Okay. Now that we're done with strong bases, we're now moving on to weak bases. Just like with the weak acids, we said Ka for weak acids tend to be less than 1. This was weak acids. Weak acids. The same concept applies for weak bases. When you're dealing with a weak base, the Kb of a weak base tends to be less than 1. So like 1.1 times 10 power negative 1, 7.3. I'm just making up numbers times 10 power negative 7. The idea is when you look at the number is less than 1, and you can tell by the Kb that you're looking at a weak base. Once again, in weak bases, only a small fraction of the molecules accept hydrogen ions. They're back to Bronsellari definition, where everything is about hydrogen ions. Okay? And so earlier, I didn't really talk about the Lewis definition of a base, but in Lewis acid, the central atom will have lone pairs. Lone pairs, the presence of lone pairs determines the basicity. Okay? And we'll define that later on. So moving on from here, once again, when you're drawing the mental model or trying to explain what a weak base is in the picture form, most weak bases, so I'll say here, most weak bases have nitrogen in them in the formula. So this is an example of a weak base. How do you know that? It has nitrogen in it. Okay. And a weak base is a weak electrolyte, meaning doesn't ionize or separate well in water. Remember, strong electrolytes are the one that ionize 100%. Then we're told here most of the weak base molecules do not accept the hydrogen ions well when they're in water. The one thing they have to do as a base, according to Bronsted Larry, they do, but they don't do well. So they're judged as weak. Okay. Example of weak bases. The most common one is the amine base or the ammonia base, and then amines. So ammonia is the term used to describe this. The amines are usually organic bases. That just means you take the ammonia, okay? I know we're going off to organic chemistry, but we have to because this class is a prequel, prerequisite, not really it's not a movie, but you know what I'm saying. This class comes before the other class. So if you take a nitrogen in the ammonia right here, so I'm drawing this formula out right here, okay? And you have your lone pair. And then you replace one of the hydrogens with a carbon with the three hydrogens around it. Because remember, right? Both carbon and nitrogen have to obey the octet rule. Nitrogen obeys the octet rule by having three bonds around it and one lone pair. So let me go ahead and recap real quick. Nitrogen has the octet rule in this form by having this is two electrons, two electrons, two electrons, two electrons. Two, four times make eight. Okay, so this nitrogen right here is obeying the octet rule. And then the nitrogen in the process of the chemical reaction replaces one of these hydrogens with a carbon. But carbon also obeys the octet rule. So when the carbon comes in, it has to come in this case, with the three hydrogens so that both of them, while they're bonded together, are still obeying the octet rule, which is true to their nature. Okay? So carbon is going to have, once again, four bonds obeying the octet rule. So when you have a base where the nitrogen is attached to a carbon, this is called the amine base. So both the ammonia base and amine base are nitrogen infused base. No, they have essential. They are nitrogen. I want to say nitrogen base, but that wouldn't really work. This is too basy, right? They are bases that contain nitrogen as a central atom. That's better, right here. So both of these contain nitrogen as central atom. Okay, and you saw how I showed you this. So essentially, amines are birthed from ammonia, but they have ammonia and a carbon, and that's why they're called organic bases. Okay, so once you get to organic chemistry, you guys will learn all this stuff there. Back to general chemistry though. So in general chemistry, we're looking at just a regular ammonia base. So the question is, how is ammonia a base? Well, ammonia is a base because it's able to take in the proton. So I mentioned this in lecture. When I was thinking about this as a student, I was trying to remember it because my recall is not the greatest. But if I put a story to it, then it's not just recalling what happened; it's just trying to tell a story. And I can tell stories better than I can recall things. Anyway, I was like, nitrogen base is kind of a bully, a little bit, okay? Because nitrogen is defined as a base according to Bronsted Lowry, right? If you look at it, can I write down here? I'll write down here. Nitrogen in ammonia is defined as a base, but it doesn't have an OH in the formula, which is okay because Bronsted Lowry never said anything about having an OH. What they said was the base has to be able to kind of catch or accept the hydrogen ion. So it's okay if it doesn't have an OH, right? Because that's all about Arrhenius. This we're looking at ammonia, the nitrogen in ammonia, and seeing if it can take in the hydrogen. Well, what so the argument here is ammonia can be a Bronsted-Lowry base, but can ammonia be an Arrhenius base? Indirectly, yes. How does it do it? It reacts with water, right? Because this is a weak base, you want to use the equilibrium arrow. Water is going to be a liquid, ammonia is going to be aqueous. Even though it doesn't come into this relationship with the OH as is required of Arrhenius base, it bullies water into giving up the OH. It's like, yo, water, I don't have OH, but you're going to produce OH. That's not really what happened. And the water is like, oh, okay, I need to stop. try to make this okay. Yeah, I know. It's just at some point this gets a little bit dry for me, so I'm trying to make it a little bit interesting. I know. So it takes the hydrogen from the water and leaves an OH behind. So even though it didn't come into the relationship with an OH, it forced the other molecule, which is water, to be the OH producer. So in the end, OH is formed in the solution when the solution didn't start off with a base that had an OH. The bottom line is when the roll call is done to see is there an OH present? Guess what? There is an OH present. Did it come from nitrogen or ammonia in this case? No, it came from water. But this is still defined as a base because its presence causes this to be formed. Okay. Once again, in lecture, I didn't have the liberty of time, so I went through this a little bit faster, but now I do have a little bit of time. Okay. So ammonia's presence causes the formation of a hydroxide ion. So technically, you could kind of argue it is an Arrhenius base. It definitely isn't a Bronsted-Lowry base because it takes the hydrogen ion, right? So ammonia is a Bronsted-Lowry base. You could argue it's an Arrhenius base, kind of, because its presence causes the production of hydroxide ion. Okay, that could be your argument right there. It doesn't come in with it, but it forces the other molecule that was already present, aka water, to produce it. Right? Whew. Yeah, that was yeah. So back to this. That's how we get the hydroxides, right? It didn't come in with the hydroxide, but when it got there, all of a sudden hydroxides are being formed left and right. But remember, we don't have a lot of hydroxides being formed, right? So let's look at this real quick. How many formulas did they start off with? I'm going to count the nitrogens here. So this is the conjugate acid, one, two, three, four. So it looks like they started off with six formulas, right? One, two, three, four, five, six. But only two of them got ionized. Okay. So we do have, let me erase this. So we do have four of the ammonias that are left intact. This one here looks exactly like the starting molecule. This did not ionize, did not ionize, did not ionize, making this a weak base. Only two of them ionized, right? Only two ammonias were willing to take the hydrogen from the water to make the hydroxide. Yeah, only two of them did this to produce that. The remaining four remained intact. So that's why this is called a weak base. Okay. The picture here, we have one, two, three, four intact ammonias or nitrogen. Yeah, ammonias, nitrogen in the ammonia. And then here we have the hydroxides, right? So once again, we started off with six amounts of the acid. Okay. When it comes to finding the pH of the weak base, they're telling you here it's similar to what we did with a weak acid. You have to use the ice table. Now, I've been using ice table for everything else, so just want to use the ice table. When in doubt, use ice. Ooh, I said when in doubt, work it out. But yeah, once again, if you're not sure, use ice table. It's just the E will stand for different things. If it's a strong acid or strong base, the E will stand for the end. If it's a weak acid, weak base, the E will stand for equilibrium. Okay? That's the only difference. Well, that's part of the difference. Strong acid, strong base don't have KBs. Well, they do technically, but we don't use them in the equilibrium process. Okay? So KB, once again, that's less than one, tells you you're dealing with a weak base. So let's go ahead and go straight to this problem here. Oh, this problem says here methylamine. Ah, this is an organic base. How do I know that? You have nitrogen, a weak base, and carbon, a weak organic base. So this is a weak base. Use Bronsted-Lowry model, write the reaction of methylamine with water. So this is, of course, CH3, NH2, aqueous. Because it's Bronsted-Lowry, you have to have the reactant and the product. You have to have both reactants, right? You have to show the one that's taking the hydrogen ion and the one that's given. Not like Bronsted-Lowry where you just write the strong base. This is a weak base, so you're doing Bronsted-Lowry, so you have to show both the giver of the proton and the taker of the proton. Okay, I'm writing it now. Yeah. Okay. Let me finish this up, right? So we're going to do this here and do this here. I'm going to have to edit this a lot before I post it. There. Okay. So I got, oh my goodness. I think I should just eat something. I haven't really had lunch yet. I don't know. You know what? Okay. So let's do this over right here. CH3 NH2 is our weak base, AQ, plus water, liquid. And then we have our equilibrium arrow. And then remember, this is the weak base, and the base is the taker of the proton or the acceptor of the proton. So it's going to take the proton from here. And when I was a student, once again, I just remembered base made OH, acid made H3O plus. So I write the ion that I know for sure is the product first. Then the rest of it, I just write, it has to fit what's missing, right? If the OH comes from here, that means an H plus was given to that. So it's going to be CH3 and H3 positive. Okay, this becomes aqueous. Okay, this becomes a weak, well, the acid, right? Acid. Weak base and the acid. Okay, they want us to write the reaction. Oh, that's pretty much it. So this is going to be the Bronsted-Lowry base, Bronsted-Lowry base, Bronsted-Lowry acid, conjugate base, conjugate acid, right? They didn't ask for all that, but I figured while we're here, let me show you guys all that. Okay, now we're going to be finding the OH and the pH of zero point 0.1 molar NH3 solution. Let me get some water here. Since we have KB and this is small, this whole number is smaller than 1, we know it's a weak base, right? Plus, it's not a metal hydroxide. Plus, it's nitrogen base. So for sure, it's a weak base. Because of that, we're going to be using, what is it, zero point 0.1? So write the KB here. KB is equal to 1.7 times 10 power negative 5. And I'm going to be dealing with ammonia, NH3 plus H2O. I'm writing this down so I don't forget. This is going to be 0.1. Okay. 0.1 molar is the initial. And we're going to have, of course, change. And we're going to have equilibrium. And what they want from us here is OH first. What's the OH ion? And then from here, we want to get what the pH is. Okay, we got this, guys. We got this. I'm mostly encouraging myself, right? Because we're getting to that 3 o'clock point for me, at least. So I'm kind of getting a little hungry. NH4 plus OH minus, right? AQ, AQ. So I'm going to draw my vertical lines here to mark these. Ignore this part. This is taking the hydrogen ion to form that, okay? Initially, we have nothing here. Then from here, what do we have? This is not a strong acid, so we cannot put 0.1 molar. No, they said it was a weak acid. The KB communicates to us it's a weak acid. So you cannot just put minus zero point 0.1. We actually don't know how much reacts, right? For right now, we don't know. We'll figure it out using the KB. So we'll write here X, and X will be a placeholder until we figure out what X is, what it is, right? For right now, we have no idea what it is. Okay. Sorry, guys. I know I'm. I have these obsessive tendencies. Okay, I'm gonna stop. So I'm gonna have 0.1 minus x, and then x here, then x. Okay. Once we find x, x will essentially be our pH, right? I'm not pH, our OH, right? Because this is essentially gonna be x. Okay. So Kb is equal to the product of the product ion concentration, which is this, divided by the concentration of the reactants. which is a weak base. Okay. Now you're plugging in the numbers at equilibrium. So this, and that here. Now before I do that, I want to check the 5% rule. Does the 5% rule pass? Okay. What was my KA? Or sorry, KB. Man, y'all, KB divided by base NH3 times 100. Let's see what it is. 1.7 times 10 power negative 5 divided by zero point 0.1 times 100. I can tell you right now, since it's power negative 5, it's going to pass. Yeah, it's passing. Check, passed. Okay, that means I can remove this part. It's only the x's that are added or subtracted to numbers, not the ones that are by themselves. So you cannot cancel this or this out, just in case you're wondering. Okay, so our KB is 1.7 times 10 power negative 5 equal. These are both x over zero point 0.1, right? I want to make sure I copy the right KB 1.7 times 10 power negative 5. Okay, so cross multiply. I'll do this part first. I end up with x squared equal, then this part here, 1.7 times 10 power negative 5 times zero point 0.1, right? 1.7 times 10 power negative 6. It's going to be x squared. So, of course, x is the square root of 1.7 times 10 power negative 6. Whew, I need to find the square root on my calculator. Where's the square root? Square 1.7 exponent negative 6, close parentheses. Did I have opening parentheses? No, delete this. Press equal. Okay, x equal 1.3 times 10 power negative 3. So according to this is 1.3 times 10 power negative 3. I have to plug this back in here. Oh, come on. I erased that. That's okay. Minus 1.3 times 10 power negative 3 plus 1.3 times 10 to the negative 3 plus 1.3 times 10 to the negative 3. Okay. 1.3 times 10 to the negative 3. 1.3 times 10 to the negative 3. I know this is so exciting. One more. 0.1 minus my answer 0.099. Okay. Now what they want though is OH, and I said OH is this number right here. So I can answer this right here and say OH ion is equal to 1.3 times 10 power negative 3 molar. Then they want the pH. So for here I have to do POH first, negative log base 10 of OH, which is negative log base 10 of 1.3 times 10 to the negative 3. Am I running out of room? Yeah, looks like I'm running out of room. Okay, so negative log 1.3 exponent negative 3, close parentheses. So POH is equal to 2.89. pH equal 14 minus 2.89. pH is equal to 11.11, right? So these are what I'm getting from my answers. Let's see what they got. Table, some more table, testing stuff. Oh, 1.3, 3 times 10 power negative 3. Kept going, 11.11. So for this part here, make sure I'm recording and the audio is on and I'm sharing my screen. For this part, we're looking at acid-base properties of ions and salts. So a little background information here. Let's go ahead and look at Arrhenius' definition. So Arrhenius' definition gives us the background of how the salt is made, right? When you have an acid, remember Arrhenius' definition says the acid has to have a hydrogen. So example here is going to be, say, HCl. This is Arrhenius strong acid. And then we take Arrhenius base, sodium hydroxide. So with Arrhenius acid, Arrhenius strong base, the acid has the hydrogen ion, the base has the hydroxide ion. From 1411, since these are both strong, of course, we're going to use a one-way arrow. From 1411, when you have two compounds reacting, we have the double displacement reaction, correct? They are both ions, or ionic compounds. So this breaks apart into hydrogen ion, chloride ion. This breaks apart into sodium ion, hydroxide ion. So before we form the products, remember the hydrogen ion is the ion that represents all acids, well, acids in general. And then the hydroxide ion is the ion that represents bases in general. So as these two are reacting, the sodium goes off with the chlorine to form sodium chloride. And essentially you have sodium ion getting together with the chloride ion, the positive ion from the second, going off with a negative ion from the first to form sodium chloride. This crisscrosses here, and we essentially get this compound, right? And then the hydrogen ion from the first goes up with the hydroxide ion from the second. We get hydrogen ion from the first, hydroxide ion from the second, and from here we get water. Okay, so from Arrhenius' definition of acid and base, we get an understanding that strong acids and strong bases usually form salts and water. Okay, our focus in the last part of this chapter is on the offspring, salt. So we're going to look at salt as the child, the baby. When the strong acid, oh, not the strong acid, but when the acid gets together with the base, they produce the salt. Okay. Now in 1411 or other chemistry classes or even biology classes, you probably heard that when the acid and base react, acids and bases neutralize each other. In other words, when an acid needs to be neutralized, bring in a base. When a base needs to be neutralized, bring in an acid. They are two parts of a whole, a yin and yang relationship in the goal of neutralization. Okay, so acids neutralize bases and bases neutralize acid. Now, of course, you can approach neutralization from the point of view of acids being positive, bases being negative. So positive and negative produce neutral water. So you can look at it that way. But most of the time, when I talk about neutralization, the terminology is focusing on pH. Remember, we mentioned before that the pH of acids is low, so less than 7. pH of bases is high, greater than 7. And when you look at the two products that are formed, if both the acid and the base are strong, the pH of the salt will be neutral, so exactly 7. And the pH of the water will be neutral, also exactly 7. So the acid, once again, is a low pH, base, high pH, and they form neutral products, both of which are neutral, right? The salt and the water. So the act of forming something that is neutral when you started off with something that wasn't neutral is called neutralization. So neutralization essentially means forming neutral products. And the context of neutrality here is the pH. If you use the pH meter or the pH paper to measure the sodium chloride or the water's pH, you will get an exact neutral solution, right? Or a neutral result. So pH of 7. Okay, now that I've presented that point, I want us to move on. So what we're seeing here is if both the parents are strong, the offspring or the child does not take after either parent, it actually represents both parents equally. So when the salt is neither acidic nor basic, it's actually both acidic and basic equally. We have a draw, so the salt ends up neutral. So I want to talk about babies and parents. Now I remember when I was a kid, people used to tell me, "Oh, you look just like your father," and I'd be like, "Yeah, I get the point." When it came to making me, my dad's DNA was a little bit more dominant. Now that I've grown up, people are telling me, "You look like your mother. You look just like your mother." I'm like, well, I guess life happened and things switched around, right? But we get the understanding when we say a child looks just like one parent, that that parent's genes are strong, right? And then the other parent, when it came to making that child, their genes kind of took a back seat, right? Sort of like that. Anyway, we'll use that understanding here when we're looking at making the child or making the salt. The child tends to resemble the parent that is stronger. In this case, the child, the salt, does not represent either the acid or the base. It actually represents both equally, not one or the other, because both parents are strong. So when you have a strong acid and a strong base, they make a neutral salt because the child, the salt, is representing both parents equally. Okay? So hopefully I've made that point. Now I can move on. Okay, so salts are ionic compounds formed by neutralization reactions between acids and bases. Salts contain the cation of a strong base and the anion that is a conjugate base of the weak acid. Wait, sorry. I have to read that over again. Salts that contain the cation salts that contain the cation of a strong base and an anion that is the conjugate base of a weak acid are basic. Okay? So what they're saying here is if you have a salt, remember the child, and the salt, for example, here is sodium chloride. Let me come and backtrack a little bit. The sodium chloride is the child, right? Sodium chloride was made from sodium ion and chloride ion. So the parent that produces sodium ion is the base, right? Sodium hydroxide had to break apart to produce sodium ion. And then the parent that produced the chloride is the acid. Hydrochloric acid broke apart to produce the chloride. Okay? So what we can say here in general, positive ions come from the base, negative ions come from the acid. So base produces positive ions in the salt, and then acids produces negative ions. Okay? So when you're trying to figure out what the parents are from the child, do some reverse engineering. I use the term reverse engineering very loosely. Just reverse the process. Remember, the base ions are hydroxide, the acid ions are hydrogen ion. So just add those to the component that came from the appropriate parent and you get the parent. So what I mean by that here is, can I work this on the side? Let me do work it over here. I don't want to pull out a new page. Since sodium chloride is the child, that means take the sodium ion. This came from the base parent, right? Add the base ion and you recreate the base parent. Take the chloride ion, add the hydrogen ion. Since the chloride came from the hydrogen, I'm sorry, from the acid parent, and you end up with the acid parent. Okay, so add the OH to get the base parent, add the H plus to get the acid parent, and essentially you have these two. So by looking at the child, you can figure out what the parents are. Sodium chloride was made from sodium hydroxide and hydrogen chloride. Okay, so that concept is important for you to understand what is written down here. So now they're saying right here, salts that contain the cation of a strong base. So cation of a strong base, that could be like sodium because the cation came from the strong base. And an anion, that is the conjugate base of a weak acid. So the anion came from the weak acid. They're just saying the portion that came from the weak acid is actually the conjugate base, the negative ion from the weak acid. That kind of salt is basic. So let's see, back to what is written here. I know the way they're saying is kind of confusing, but let me show you a simpler way to understand this. Salts that contain the cation of a strong base. I'm going to pick a strong base like sodium hydroxide. Actually, you know what? I just thought about something. I keep forgetting the kind of things I can do with this app. Let me use this right here. I'm trying to explain this, so I'm going to copy this into a new page. That way we can focus on that, just that alone. Oh, right here. We're trying to focus on the terminology. Okay, maybe I should paste image. There it is. Okay, so now that we have this, let me make this bigger here. Let's get our strong base. So we're going to do a strong base. I'll choose sodium hydroxide. And then we're going to pick a weak acid. Weak acid, let's take hydrogen. So weak acid. Weak acid. Let me pick the one that they picked. They picked carbonic acid. So they use H2CO3. Okay? So we have our two ingredients, strong base, weak acid. So the salt that contains the cation of a strong base. So let's get the cation from here, ionize it. We need just the positive ion, sodium, the first one, right? And then we need the anion to come from the weak acid. So from the weak acid, separate the H plus from the rest, HCO3 minus. And this is the part that we need. So we need to combine the anion from the weak acid, the cation from the strong base, and we get our salt. So now we can go back and read this statement, right? So these two make up our salt, and our salt will look like this, sodium bicarbonate, right? Because you essentially took the sodium ion, combine it with the carbonate ion, and then you crisscross this to get this compound. Okay, so when you have a strong base, we know it's a strong base, and a weak acid, the salt that is made is basic, a basic salt, because the salt's identity is tied more to the stronger parent, or I guess the salt's nature, right? Whether it's more acidic or it's more basic has to do with which parent is stronger. So we have a basic salt here. And then the other thing I want to point out is they use the term the anion that is the conjugate base of a weak acid. Notice this anion here. This is actually a conjugate of this, because remember, the conjugate is what is left behind once a proton is removed. So this proton was removed from the formula, and this is technically a conjugate base. Why they had to say all that, I don't know. They just said the base ion, but I understand why they're saying it though. I do understand. All they're saying is remove the hydrogen ion, what's left behind, which is also called the conjugate base. That's the anion you need. Okay? So we're done with this concept here. Once again, sodium ion is the cation of the strong base. Uh, bicarbonate ion here, or hydrogen carbon, is the conjugate base of the weak acid. And of course, together, they make up this salt. Okay? So that's rule number 2. Rule number 1 is, of course, if a salt is neutral, if both the acid and base is strong. The second rule here, a salt is basic if the base is strong and the acid is weak. Rule number 3, salts that contain cations that are conjugate acids of weak bases and an anion of a strong acid are acidic. So like before, let me take the statement from here. We're going to break it down and figure this out. So I'm going to copy this from here. I'm going to copy this, copy, paste this image here, zoom in. Okay, so we have salts that contain cations that are conjugate acids of a weak base. So in other words, we have a weak base. And for my weak base, I can pick NH3. What kind of weak base do they have here? Okay, I'll pick NH3. And then I need a strong acid. My strong acids to match what they have is HCl. Okay? So salts that contain cations that are conjugate acids of a weak base. In other words, the positive ion in the salt, the cation in the salt, the first ion in the salt is actually a conjugate acid of a weak base. So then your weak base, add an H plus to it, and you end up with an H4 plus. So this is your weak base here. When you add the H plus, you end up with a conjugate acid. So all of this is trying to say, if your salt has the cation ion and positive ion, well, the positive ion is technically a conjugate acid from a weak base, and it's combined with the anion from a strong acid.
This is going to be acidic salt. So let me try to get the here minus the H plus, right? We get L minus. Once again, it's a strong acid. This is a conjugate base. So you're combining this and this, right? So NH4 plus Cl minus make up NH4 Cl. Okay? So this is just saying, take your salt and get the parents from the salt. So the parent here is gonna be this is the part that came from the acid. Let me highlight. You know what? Let me try to make this a little bit fun. Can I highlight that part here? Let me see if I can highlight. Where do I get my highlight from? It's a little bit darker than I want to. Can I get a lighter blue maybe? Give me a moment. I'm trying to make this a little bit exciting for me. Okay, so the ammonia part, this first part comes from the base, right? So to get the base, you're just going to add OH, and you end up with ammonium hydroxide, which with this one, if you subtract water, you end up with NH3. But here's where I want you guys to look at this so it's not complicated. Ammonium hydroxide is just ammonia in water. So if you get the ammonium hydroxide, just judge this as being a weak base, because I mentioned before that weak bases have nitrogen in them. So add the hydroxide here, get this, and make a judgment. This is a weak base. Then move on. Don't overcomplicate it. Come over here to the Cl minus. This is the acids. I'm going to paint the acid pink. Why? Just because. The acid portion. For the acid here, add H plus, right? So we end up with HCl. What is this? One of the 6 strong acids. Strong acid. So if you have a salt where the anion came from a strong acid and the cation came from a weak base, then the strong component controls the nature of the salt. So this is going to be an acidic, if I can spell salt, okay? Because this is strong. So acidic salt because the negative ion came from a strong acid. Remember your 6 strong acids, right? HCl, HI, HBr, H2SO4, HNO3, HClO4. I'm trying to think about something else, but yeah. So let me make sure I've gone through all the rules here. Yeah, so we're moving on to the next rule. And the next rule here is saying, of course, um, there is more to it than that. I have talked about this rule already. If the cation is a counter ion of a strong base and the anion is a conjugate base of a strong acid, in other words, if both the base and the acid are strong, you end up with a neutral solution or neutral salt. These are all neutral because all the parents are strong. Okay? So let me try to show you that real quick without overkilling the point. Okay, so I'm going to start with here. NaCl. Add the OH to get NaOH. Add the H plus to get HCl. Strong acid, strong base. Okay? So that makes this neutral. Calcium nitrate. Okay? Add the OH minus, you get calcium hydroxide. So go back to the lesson. You can see this is actually a strong base. Add the hydrogen ion. This is going to be nitric acid. Strong acid. You end up with strong base, strong acid, neutral. And that's true of this one too, right? So I won't do that one because I feel like I'm overstretching this lesson. Let's go through here. I'll pick 2 to show you how this is weak. I'm going to pick the first one and the last one. For sure, this is a weak acid. This is not even one of the 6 strong acids, right? Or, yeah, I'll pick those 2. So sodium fluoride. Wrong marker. Sodium fluoride. What was the other one? KN O2. Once again, add OH, add H plus. You end up with HNO2, not HNO3. This is a weak acid, right? This is a strong base, KOH. And over here, add OH, add H plus. You end up with HF, NaOH. This one ends up being a strong base, weak acid. Since the strong part is the base, it's going to be a basic salt. This is strong basic salt. Once again, the strong parent dominates. Okay? Oh, give me a moment. I was just suddenly got warm here. Okay. So we're moving on and we're going into the next part. The next part of the slide here shows us uh, this scenario here where you have if the salt cation is the conjugate acid of a weak base and the anion is the conjugate base of a strong acid, the cation is acidic and the anion is pH neutral. Therefore, an acidic solution is formed. Like we mentioned before, this part here comes from a basic, from a weak base. Sorry, basic, a weak base, and this part here comes from a strong acid. So this would be an acidic salt, right? The next rule I want to talk about that I haven't discussed yet is if you have a salt cation that is highly charged will be a charge of maybe +3. They should just say +3. A highly charged metal ion. And then the anion is the conjugate base of a strong acid. The salt will be acidic. So the example here we have is aluminum nitrate. If salt has highly charged cation. So the highly charged I'm seeing here is a charge of +3, right? So like aluminum is 3 plus, maybe even iron 3, anything that has a 3 or even +4, like +3 up, right? And combined with the anion from a strong acid. So this is from a strong acid here. And then let's say Br from a strong acid. This salt that is formed, aluminum chloride, this is an acidic salt because once again, you have a strong acid. Here we have a strong acid. So this would be FeBr, FeBr3. So Fe3 plus Br would be FeBr3. This would be also an acidic salt because the salt has a highly charged cation. This is a cation and the charge is +3 +3. Okay? So what happens if both parents are weak? If both parents are weak, like in the case of NH4F, this comes from, I'll put an H plus here. HF is a weak acid. This comes from a weak base, where it's like NH4OH or NH3 in water. How am I writing water as OH? I don't know. I'm trying to get through the lesson because I have a meeting that's coming up. So here, so this is it, right? This is a weak base. So we have both parents being weak. So which one dominates? For this part here, they actually ask you to go, wait, they didn't do it back here. They have you go through that table, this table right here, and look at which formula appears further up. We have ammonium down here, and this that's further up. So the species that's further up influences the child the most. So in this case here, we see that HF will influence the child, so we'll end up with an acidic salt, right? Because the acid portion is relatively stronger. So you'll use that table right there and it tells you which is stronger. So this is going to be relatively stronger acid compared to the acid component of the NH3, which is NH4 plus, right? So the salt will be acidic. Okay. Down here, we're going through the problems and going through the rules, and they're asking you determine if the solution formed by each salt is acidic, basic, or neutral. Okay, so let me go ahead and copy this part right here, and we'll go through the rules. Actually, the last one is exactly what I just worked out, so I want to work that one out first. Okay. Oh, I need a blank page here. Okay. I'll start with the last one. The last one, NH4 F minus. We just worked on that one where we saw that HF is the acid formed from this when you add H plus here. And then this one here, when you work it out, you end up with the NH3, right? So this is a weak acid, weak base. So you try to get the acid version of the weak base, right? Compare just this part here with this. If you look at the chart, this is further up, which means it's stronger. And remember, ultimately, the stronger parent influences the child, so to say, or the salt. So this will be acidic based on what we just covered, right? You can compare this and this or this and this. Either one gives you the same answer. It's going to be acidic. Okay, then let's start with part A. So this part is done, right? Acidic. With part A, once again, you have strontium chloride. Add H plus to get HCl. I'm not really balancing the equation here. Add OH minus to get SROH. 2. This is a strong acid. This is a strong base because this is a group 2 hydroxide, right? So if both parents are strong, we end up with neutral. All right, here, neutral. First one done. The second one, aluminum bromide. So if you reverse crisscross this, you end up with Al3 plus Br minus. Since this is a highly charged highly charged cation, it's gonna be and then this is from a strong acid. This would be acidic salt according to the rules. So I write here acidic. Okay. Then for the next one, we have what? Let me try to zoom this out. CH3, NH3, NO3. C. CH3, NH3, NO3. So for this part, it's a little bit tricky because you're looking at the organic molecule and you're thinking, there's so many central atoms in this, right? How do I separate this? So what I tend to do, what I used to do as a student was I found the ion I recognized. I mean, the easiest ion to recognize is the strong ions first before the weak ions, right? I recognize NO3. NO3 comes from, when I add H here, it comes from HNO3, one of the 6 strong acids, right? So that's one part of the formula. All of these go off together as another part. So those go off together as CH3 and H3 positive. So this is obviously a weak base, right? Remember the amine bases are weak. The nitrogen bases are weak. This is one of the 6 strong acids. So if this is stronger, this is going to be an acidic salt. That's all we're trying to define here, acidic or basic. Acidic, according to this. This one here, according to this. This here, according to both, right? And then we have nacho. It's not really nacho, but you know what I mean. Sodium, this is part D. Sodium, CHO2. And then this one here, of course, add your OH, and we get sodium hydroxide, which we recognize, right, as strong base. And then here, just add the H plus, and then we get HCHO2. And this is an acid, right? Because remember, we're trying to make an acid. We don't recognize it, so we're just going to call it a weak acid because the weak acids are not part of the 6 strong acids. So this is a stronger part, making this a basic salt. So neutral, acidic, acidic, basic, acidic. Okay. So we're finally getting towards the final part of the chapter. Acidic, basic, and then of course you have that one more. It's going to be acidic. I don't know what all of this was about. It's unnecessary. Finally, the Lewis acid base theory. And this is where we're going to be ending, right, with this section. And this section introduces you to Lewis acid base theory, which you're going to be focusing on if you're taking organic class. With Lewis's acid base theory, we're told here we're focusing on the transfer of electron pairs, right? So we're going to be seeing in the reaction mechanism, which they don't tell you here, you just have this arrow and you're like, what does this stand for? But in the mechanism, as the bonds are forming, we'll see lone pairs becoming bonds and bonds becoming lone pairs as needed for the chemical reaction. So this is a play by play, right? And in organic chemistry, reaction mechanism is a big deal. Not to say it's not a big deal here in chemistry, Gen Chem 1 and 2, but we tend to focus on mechanism more in the intermediate state. Remember that chapter kinetics, intermediate, first step, intermediate, whatever, overall, whatever, catalyst. That was where we focus on mechanism. But in organic chemistry, mechanism is key. Okay. As we're defining the acid and base, we're seeing that the acid does not require hydrogen atoms. So to classify an acid as an acid, the acid does not have to have an H to be classified as an acid. So what is the Lewis base? Electron donor is called Lewis base. Electron pair donor, not just electron donor, right? It is electron rich chemical species. It is often referred to as a nucleophile. So we know what the word phile means, right? Phile is a preference, a lover of, desires. So we're now trying to make the elements like people, like they have a preference. Lewis bases have a preference. They prefer nucleophile. What is so unique about the nucleophile? Let's go back to the nucleus. In the atom, the nucleus tends to have a net positive charge, right? Because you have protons in there that are positive, and then you have neutrons in there that have no charge. So the overall charge of the nucleus is positive. So when we're talking about nucleophile, we're really saying positive lover. Okay? We're judging a Lewis base as a lover of that which is positive. That makes sense because you know that song Opposites Attract? I'm sure it's a song somewhere that somebody sang, right? The Lewis base is rich with electrons, so the Lewis base is somewhat negative, and the nucleus is positive. So it is drawn to the nucleus because there's an electrostatic force drawing them together. Okay, and Lewis is full of electrons. It's rich, so it's a lover of that which is positive, which is the nucleus. Here you have the Lewis acid defined as electron acceptor. Lewis acid knows its situation. It's poor. It's electron deficient chemical species. It's poor. Okay? So it will accept electrons from the Lewis base because that's what happens. And then it is referred to as an electrophile. Once again, it's the lover of, seeker of, it prefers that which is rich with electrons. Rich with electrons. It loves that which it does not have. Okay? So, electron poor, electron rich. So, in this chapter, as a student, I noticed this, right? In the other two definitions, the aggressor was the acid. We tend to talk about the acid first. In this chapter here, though, sorry, in this section, the aggressor is the base, right? And I told you guys a story in class where I said that did I get this in organic chemistry? No. I mean, I got it eventually, y'all. Learning is a journey. But in the beginning, like organic one, I took an exam and we're showing mechanism, right? And I made the acid the aggressor because everywhere else I had seen the acid, it was the aggressor. So I drew the arrow saying the acid took electrons from the base, and my teacher marked it wrong, wrong, wrong. I mean, I still got a high grade, but he counted me off so many points for the arrow going the wrong place. It was going between the right chemicals, but I made the acid the aggressor. So apparently the base is the aggressor. And that's it's important for you to state that. Okay? The one that has the electrons approaches the one that doesn't have electrons.
So I'm letting you know this, okay? I wasn't traumatized by that one because I didn't really do very badly. If, Let me tell you something. If that same exam was back at home, I would have failed that exam because all my arrows were making the acid the aggressor. But there's more grace here, so I just take the grace when I can get it. Okay. So we're starting with the acid, but remember, it's the base that's the aggressor. The acid is the one that's electron pair accepting, right? So we're told Lewis acids are electron deficient, right? They're electron poor species due to being attached to electronegative atoms in a bond or as a result of not having a complete octet. Okay, so this is the chemical definition of a Lewis acid. Of course, I like backstories because I'm like, wait, if the Lewis acid is poor, how did the Lewis acid become poor? Because elements all start off with a certain number of electrons. They may not have an octet, but they just have a certain number of electrons, right? So we're being told here how you can end up as as an element, how you can end up poor. You can end up poor. So let's talk about the backstory of poverty as far as the elements are concerned. Lewis acids and how they become electron poor. Number one, they can become poor because they just gave away electrons. Or you can say lost electrons. You lose your money, you become electron poor. Sorry, you lose your electron, you become electron poor. You give away your electron, now you don't have electrons, right? This is how you end up as a Lewis acid. Example, hydrogen used to have one electron. If it gives its electron away, it becomes hydrogen plus, right? The plus here indicates that it did have it, but now it doesn't because it gave it away or it lost it. Same thing here. Sodium can have a bunch of electrons, but if it gives away one electron, now it is. So these two are electron poor species. Aluminum, of course, sodium is in group one, so I'll put one here. Aluminum has three valence electrons. If it gives all three away, guess what? It's poor. And you can see right here, according to Lewis, this one here is very poor. So these are all Lewis acids. Okay, so that's one way to become electron poor or electrophile, the lover of the electrons. Man, I'm forgetting my organic words, y'all, from not teaching organic for so long. No, don't even say it. Don't even think about it. Okay, next thing is the attachments you form in life. I'm sorry, y'all. I have to make a life lesson from this because when I was learning this stuff, I was like, oh, this reminds me of my life, right? Being attached to electronegative elements. Okay? So remember, electronegative elements for the most part form covalent bonds, right? As in the bonds that are formed from sharing. So let's look at an example here. Carbon dioxide. Carbon dioxide Lewis structure looks like this. Ta-da-da, okay? Carbon formed double bonds with each oxygen by sharing electrons, right? But we know from period 2 in the periodic table that these groups here, while they follow the octet rule, fluorine is the most electronegative. That means when carbon and oxygen form a bond, oxygen will pull the shared electrons to itself. So between this carbon and that oxygen, the electrons are being pulled by the oxygen on either side. So carbon is facing the pulling twice. Each oxygen is pulling electrons to itself, right? Making that carbon partially positive. So even though it technically still has its electrons, but the carbon is now partially positive because of the two oxygens on either side pulling electrons. So because of that, we're seeing that this carbon becomes the carbon, not the oxygen, becomes what is it called? A Lewis acid site because the carbon is attached to two oxygens on either side that are pulling electrons away from it. It still has access to the electrons, but they're spending more time on the oxygen side because of their electronegative privilege. That's not really the privilege part is not a thing, but I'm trying to add emotions to it so you understand, right? Some elements just have that privilege because of their size. They're smaller in size. So in this case here, both oxygens are pulling electrons away from carbon, making it more positive. So if electrons are to be given to either one of these, the one that has can accept the electrons will be the carbon over the oxygens. Okay. Once again, I'm trying to use organic examples to bring in the future into the present. Moving on. Another way you can see this also, and the example is oxygen and hydrogen. You see this in organic too. Oxygen and hydrogen. Once again, the oxygen pulls the electrons away from the hydrogen. Even though the bond still exists, the oxygen is partially negative, the puller of electrons, electronegative, and then hydrogen becomes partially positive. Okay? So this one here becomes the Lewis acid site, the one that can take in electrons. And the way it takes in the electrons, it says right here, by forming a bond. Okay, so the way it's taking electrons is forming a bond with the giver of electrons. So they form a bond. Okay, so when I was learning this, of course, I was thinking, I was like, you know what? There's some people in life who go after, like when it comes to marriage and relationship, there are people in life, I won't really label them and call them, files, but they go after people who have, if they don't have money, they go after people who have money, right? And the people who have money sometimes want people who don't have money so that they go after them. As long as their goals are matched, right? I shouldn't say matched. If the goals are compatible, the one going after the one that has money, right? And that the one that has money is okay being with the person that doesn't have money. I feel like their goals are aligned. In this case here, you have the Lewis acid that is electron poor going after, actually, it doesn't go after, it waits for the Lewis base that's electron rich, and the Lewis base approaches the acid. Okay, I'm saying it this way because I was told no, 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 and I have not forgotten. It's been so many years since I was in school. I know. I should move on already, right? Number three, this I think is the last way which the elements can end up poor. They're just naturally poor. I want to say they're born that way, but the elements are not really born, right? So I don't want to say, I just want to put it here, but y'all know, come on, they're not born, okay? But let's just say they're born poor. For example, boron. Technically, this applies to aluminum also, right? Group 3 elements, group 2 elements, group 1 elements, they just don't have, even in their bonding, they're not able to get to octets. So these have an incomplete octet. So even when they bond, they don't get to octet. So even when bonding, they have empty orbitals where electrons could go into. Okay, so let's look at bonding with boron. Boron with three hydrogens. This is the best that boron can do. This is naturally how it is. Okay, there is an empty orbital here that should have a bond, that could have a bond, but it doesn't. So when you encounter boron with three hydrogens, boron is poor. It's a Lewis acid because that's just how it is. It's poor. Now, can it bond with the Lewis base? Yeah, it has room for it right here. This is the room for lone pair electrons, right? Another one, aluminum. I'll put aluminum chloride. Cl, 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 dot, 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 dot. Emptiness here. Okay, once again, room for electrons. This is a Lewis acid. It is what it is. That's just how it came into the world, right? Aluminum comes in and has a
emptiness in here. Once again, this is me as a student saying, you know what? I've seen this in soap operas where some people just, emotionally are in a relationship. Sometimes emotionally, sometimes financially. Once again, where one provides everything, the other one is just a taker. And the one that's a giver, usually they feel value in being able to help other people. So it's not just transactional, right? But the giver feels value in being able to help other people. And then, of course, the person that needs help, right? They're trying to meet their needs. Sorry, I'm talking about people, but you know what I mean, right? I'm just saying, as a student, I was like, oh, I didn't know elements did it too. Okay. So we've seen three different ways in which the acids, Lewis acids, are formed, right? How they end up electron poor. So over here, of course, they're gonna go over it. It won't be as dramatic as what I've tried to present here, but they must have an empty orbital. The Lewis acid has to have an empty orbital that's willing to accept the electron pair, or else you gotta have a place to park the electrons, or else you can't be a Lewis acid, right? They're telling you here, H plus has an empty orbital. It gave up its electron. The boron in BF3 has an empty 2p orbital and an incomplete octet, right? Once it makes that bond with the Lewis base, it becomes complete. Y'all, in no way is this trying to advocate or say that you are incomplete until you get in a relationship. This is talking about elements. It is for real. I'm just laughing. Leave me alone. Okay. Many small, highly charged metal cations have an empty orbitals, and they can use these empty orbitals to accept electrons. Okay. Atoms that are attached to highly electronegative atoms and or have multiple bonds can be designated as Lewis acids. And I showed you guys that with CO2, right? So I've seen three different ways in which an element or compound becomes poor. Then we're moving on to Lewis bases. These are the electron pair donors. They're just rich. A Lewis base species has electron pairs that it is willing to give away or to share with another atom that is deficient in electrons, right? This is a giver of electrons. A Lewis base must have a lone pair of electrons on it that it can donate. Anions are better Lewis bases than neutral atoms because anions have that extra lone pair of electrons, right? So let me try to show you this in an example that makes more sense. Okay. Let's talk about the making of a Lewis base. I like backstories. I just like stories, period. And as we're going through this part here. I'm trying to narrate it and hopefully add a little bit of drama. This is the drama that I like, not actual people drama, but elemental drama. So let's talk about this, right? I'm going to look at water and talk about what form of water is a good base. So we have water, right? Lewis structure. This, this right here, lone pair. Okay, we can classify this as a decent base. So right now, I'll just say it's a base according to the fact that it has lone pairs. Okay, so I'm gonna highlight the feature of water that makes it basic. Okay, then I'm gonna remove. So from here to the next one, I'm gonna remove a hydrogen ion. So we end up with oxygen being left with one bond, and then it has an extra set of lone pairs. Okay, a hydroxide. This, of course, becomes a better base. Why? It has an extra pair of electrons. Okay, then from here, I'm like, this is good, but I think it can be better. Can it be better? Sure, I say. Can we make this hydroxide any more basic? Sure. Let's remove the last hydrogen. Can we do that? Yes, we can. Remove the last hydrogen, and now we have four sets of lone pairs. This is going to be -2. This is oxide. Like from 1411, oxide O2 minus. This is it right here. So this is oxide, hydroxide. Yeah, y'all are going to encounter this in organic. I'm trying to channel my inner organic. And then water. I remember having to organize this according to the basicity. Of course, of these three, this would be your strongest base, right? This of the three will be your weakest base.
I mean, because in the world of electrons, it only has two sets. That's like being a 2 billionaire. That's not really a thing, but you just have 2 billion in the group, right? Here they got 3 billion. If each lone pair is a billion, and then this one here has got 4 billion, who is richer? The one that has more billions, right? The electrons here are what makes the species a base. This one is the strongest base because it has four sets of electron pairs, right? Okay. I actually think this is very, you can tell my energy, right? I definitely think this is interesting, right? So much drama, so much. Okay, so back here, then, if that applies for that, when I look at this picture here, I'm like, there's a lone pair missing, y'all. Why are you missing a lone pair? Because how can I just look at that and be like, oh, negative is richer? You got to show the lone pairs. Please notice right here, there's a point I'm trying to make. Anytime a bond, so this is a Lewis structure, right? I remove this bond here and replace the bond with a lone pair to make this. If you go through the process of drawing the Lewis structure, you get a hydroxide. From here to here, you get a hydroxide. When you remove the second bond, this right here, you end up with -2 charge. So remember, you're going from, is it -2, -1? I've forgotten how to write. Hold on. 0 plus 1 plus 2. So each time you're removing a hydroxide, sorry, a hydrogen is becoming more negative, right? So we started off with water that was neutral. Remove a hydrogen minus H plus. Remove a hydrogen minus another H plus, and we're here. Of course, you have -3, where you can keep going, right? But in our case here, we did this twice. So we went from water that was neutral to hydroxide, that's -1, to oxide, that's -2. That's how it works with the charges. By removing something that's positive each time, you're going more negative. Okay? So over here, by removing a hydrogen ion, going from here to here, you're becoming more negative. So of course, I know I over explained that one. Here, this is going to be a strong base compared to this. You have an extra lone pair. Now with this one here, they're saying that generally this has a group relationship, right? You have oxygen, sulfur in the same group. Generally, the more electronegative an atom is, the less willing it is to be a Lewis base. I was like, they done did it again. Really? Electronegative is called negative. It's got electrons, but it's like, I'm not sharing it with you. I need my electrons myself. I'm going to hoard all my electrons to me. So this one here is more electronegative. It has electrons, same amount as this one here. Remember, these are both in group 6, right? So if they're forming a bond with hydrogen, it would be like this. Sulfur forms two bonds, one with each hydrogen and has a lone pair. Oxygen, two bonds, one with each hydrogen has a lone pair. So they have the same bonding ability. This one here just refuses to give up its electrons because it's more electronegative, the central atom, that is, right? Sulfur, on the other hand, is like, I'll share it with you, right? And that's how this one here ends up being more basic. So you want to remember that rule. Oh, we're close to the end. Okay, now we're seeing the reaction, the Lewis acid and base reaction. That has to be labeled because if you take this away, what is this? Makes no sense. This only makes sense if it's you're looking at it from the point of Lewis. Okay? So Lewis acid base, it says here, Lewis base donates a pair of electrons to the acid. So when you see something like this, draw the Lewis structure. I know, Lewis. So you can see what's going on. We see nitrogen. Ooh, I need to wrap this up. I have a meeting, y'all. And I've just been going on about all this drama with these elements. Draw the Lewis structure and you see here, there's a missing orbital. Sorry, not missing, but empty orbital right here. I'll draw the box. It's an empty orbital. And this is, so this is going to be Lewis base forming a bond with the Lewis acid, right? And that's the bond that forms right there. And so the product here is not salt and acid. This is called an adduct in general because these two are adding to each other as the nitrogen is reaching forth to help the boron. Okay? We're seeing this worked out in organic chemistry. Now, When in doubt, start with the central atom, right? We can see here the central atom aluminum is missing an octet. This one here has a lone pair. So this becomes the aggressor to go after the aluminum, and it fills that emptiness in the aluminum's core, right? And this is pretty much, this becomes the bond between the two. And this is the product, the adduct, because the two are being added to each other. When it comes to organic chemistry, so this is more like Gen Chem. In organic chemistry, Gen Gen Chem 1, Gen Chem 2. We're looking at it in Gen Chem 2, so Gen Chem 2. This is an example of organic. So I'll call this Orgo for organic, right? Once again, you see the arrows? Y'all now see the arrows, right? Don't be like me. Don't be like me. Because I drew the arrow here. I figured if you can draw it one way, you can draw it the other way. Teacher said no. Okay. The aggressor is the one that has the lone pair electrons, right? So start with the central atoms. This is the first move first. So the lone pairs are used here to make a bond with a carbon. Even though carbon already has octet, carbon is partially positive, right? Remember, because it's attached to two partially negative atoms. And then this one here is Lewis base, and it's also partially negative, right? Compared to the partially positive here. So the negative goes after the positive, and that's what forms this bond right here. Okay? Now we know from 1411, the elements snuff, these obey the octet rule all the time. So I'm going to count here. Watch this. One, two, three, four. One, two, three, four. Carbon already had four bonds. So if you leave that fourth bond here, carbon will now have five bonds, but carbon cannot have five bonds because it's part of a group that always obeys the octet rule. It has to keep that four bond thing going on. So what happens here is, in order for it to keep the four bonds, since this bond has to form here, this bond then has to break. You see this bond here? This has to breaks to keep octet. So it breaks. But when it breaks, the bond becomes lone pairs. Okay? It doesn't just break and disappear. The electrons that were shared between these two get broken to help carbon maintain the 8 octet, because carbon is essentially breaking this bond to pick up this bond here. Okay, hopefully you can see that it picks up this bond, but it breaks this bond in the process. Now oxygen, I used to say, doesn't feel comfortable that way. Oxygen wants to have two bonds and two lone pairs. So it decides to form a bond. It uses up the two electrons to form a bond with this hydrogen. Now remember, at this point here, temporarily while this is happening, because oxygen broke a bond, it becomes negative, right? So it becomes a strong Lewis base. And it goes after this hydrogen that is positive. Remember back here we said it was positive? It's still positive. That hasn't changed. So this goes after that, using the electrons here to form a bond. When that happens, a new bond forms here. Now this bond has to break, so the hydrogen doesn't have two bonds. Y'all need to review bonding for 1411. So this bond breaks here, and in doing so, now oxygen, remember in the middle here, oxygen had three bonds, and actually ends up being, yeah, let me leave it like that. Oxygen has three bonds here. So we see here that this bond has to break to to reform the lone pairs. So this bond breaks, the lone pairs are formed. These right here are the lone pairs that got formed when the bond broke. And then the breaking and the forming of the bond stop. And let's try to make sense of it. It stops because the oxygen now has a structure it's comfortable with, two bonds, two lone pairs. The carbon has a structure it's comfortable with, four bonds, right? Nothing really happened to this. It didn't change at all. This oxygen has a structure it's comfortable with, two bonds, two lone pairs. The hydrogen has a structure it's comfortable with, one bond. And so this becomes the product formed right here. And this is called carbonic acid, essentially H2CO3, right? These two are the acidic hydrogens, and that's the organic compound formed. Okay? So this is a review. How did this end up down here? This doesn't really belong down here.
Let me delete that. This slide does not belong down here. Delete that. And so right here, when we're reviewing these problems right here, it says label the following as Lewis acids or base. Do we have one that goes with the chapter? We should have one that goes with the chapter, right? Something happened to where that one disappeared. But let's go through this. If you draw the Lewis structure here, this is going to be P, H, 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 lone pairs. So this is going to be Lewis base because of that. This one here, we know boron has less than oxide, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The emptiness here makes it a Lewis acid. Cobalt, it got poor because it lost 3 electrons. It has empty orbitals. Lewis acid. H, S being negative means it has an extra pair of electrons besides the regular 2. So this is going to be Lewis base. So by looking at this, we can see that, yeah, this is definitely very rich with electrons. So base, acid, acid, base. Okay. And this is something that I went over before. Let's see. I won't go over this part here because once again I have a meeting to go to. What I'm going to do is try to. I mean, you can see the answers here, right? This has to do with more oxygens, making this more acidic. This one here is one of the 6 strong acids. More hydrogens, making it more acidic. The order here based on the group number, not group number, group relationship. The further down the group, the more acidic for binary acids. Here, this is still a binary acid relationship, right? So this is more acidic because it's further down the group. This one here is across the period. This is the most acidic. This is actually a weak base, remember that? This is oxy acid, and oxy acid is the one that's further up the group is acidic. So in this case, this is further up the group for oxy acid. For these ones here, the number of oxygens are highest with number 7. So no, not number 7, sorry, the first one. So this one here is most acidic. It tells you the reason why when you go through here, number of oxygens. This one here, number of hydrogens, this is most acidic. This one here, this is acidic because it's one of the 6 strong acids. This one here, let's see, group relationship, right? Where, oh, forget that. This is most acidic because it is one of the 6 strong acids. I try to find the easiest way to figure out the answer, right? You can look at group relationship, but this is most acidic because it's one of the 6 strong acids. And it's further, it's not really even group relationship. This is more period relationship. It's further right, correct? Okay, with this one here, let me work the weird ones real quick, the different ones. Of course, this would be H plus Cl minus, Ca2 plus OH minus, H plus CHO2 minus, H plus PO4 3 minus, strong acid, strong base, weak acid, weak acid. So you go through all of this and essentially, review your notes and you can answer that part. I think this is pretty much it. Okay, I made it to the end. Okay, all the best, y'all. The next chapter is chapter 17.